So now we're finally moving into some applications of Calculus 3 and some of the multivariable calculus things we do. And this is one of the really fun ones. We're going to start with semi-boring stuff, and then the next lesson is about super fun stuff. This is all about rectilinear motion and projectile motion using vector-valued functions. So last year in calculus, you did rectilinear motion where you did, you're throwing a ball straight up and down. This year, we can do things like the path of a baseball because it not only goes up and down, but it goes forward and, potentially backwards if you were doing, say, like a boomerang or something. So Calc 3 affords you the opportunity to really look at projectile motion in a three-dimensional context instead of a two-dimensional context. So a lot of the things are the same as what you saw before in BC calculus, where you had position, velocity, acceleration, and speed. Position was r of t, and that was basically your original, for lack of a better word. Velocity was then the derivative. So the derivative of r would be the derivative of r as a vector, and you get another vector-valued function. And acceleration, the second derivative of r, another vector-valued function. Speed, on the other hand, used to be the absolute value of velocity, and now we've slightly tweaked that, and we're calling speed the magnitude of velocity. However, I have to mention that technically absolute value has always been a magnitude, so sometimes you'll see absolute value instead of these double bars. You'll see that because those bars have always went magnitude, because when you take like the absolute value of -7, what you're really finding is what's the distance between 0 and -7? What's the magnitude of the vector connecting them? So yes, although now we're calling it the magnitude of v, it's still technically the absolute value of v, and they are very similar. So I digress. Long story short, position, derivative velocity, second derivative acceleration, magnitude of velocity is your speed. So let's say I have a path down here, and it tells us to find vector-valued functions that represent velocity and acceleration, find the expression for the speed, and blah, 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 blah. So r of t is this, t squared minus 4i plus tj, and it is drawn over here. And what I first want to show you is pictorially, what do velocity and acceleration look like on the graph? So if your vector-valued function for r is this guy right here, we would have, here's the path of whatever is moving. Velocity is really, if this were, say, a roller coaster and you were on the roller coaster and all of a sudden the track ended, I know that's morbid, but just go with me here. What way would your little roller coaster cart travel if the track suddenly ended? So if I'm going on the roller coaster, and as I'm going straight up, the track ended, I'd shoot straight off like that. And then if I'm going this, and then the track ended again, I'd go straight this way. Your velocity is tangent to your vector-valued function. Now, that might make you think, oh, well, if velocity is tangent, is acceleration normal to it? No, it is not, unfortunately. It's not that simple. But acceleration does point inward from that same point, but it doesn't necessarily have anything specific going on with it. All right? So, pictorially, that's what velocity and acceleration look like. Speed would look like the magnitude of the arrows that I just drew. So, again, here's r of t. It represents my position, and it said give us vector-valued functions that represent velocity and acceleration. So, my velocity, v of t, would be r prime of t, which would be 2t comma 1. And then a of t, my acceleration, would be the second derivative of r, giving me 2 comma 0. And you can see that in the graph because these arrows point in exactly the same direction and they do have the exact same length. And then last but not least, speed is the magnitude of velocity. So if we want to call this like s of t with no vector on it, because it's not a vector-valued function, my speed function would be the magnitude of the velocity function, which is 2t squared plus 1, or if you want to call it 4t squared plus 1. Then it says calculate r of 2, v of 2, a of 2, and speed. So I'm just going to do that, and you can see it on the picture over here. So r of 2 is what I get when I plug 2 into R, you know, duh. So that's 0, 2. And then V of 2 is what I get when I plug 2 into V, again, you know, duh. That's going to be 4, 1. A of 2 is 2, 0. Don't have to plug anybody in there. And then speed at 2 is going to be the square root of 4 times 2 squared plus 1, which is radical 17. And I mean, that's really it. So if I come down here, find the vector valued function that represents the position of a particle, get the velocity vector, speed, and acceleration vector at 1, we're just going to do the same thing. So if you want, just do this off to the side on your own. You don't really need me. I'm going to do it over here quietly. And, you know, let's me. So what you just saw me do there very quickly, and again, I wanted you to do that on your own, what you just saw me do there is just take the derivatives. The only derivative here that was kind of tricksy is when you take the derivative of t e to the t, you need to use the product rule, but I mean, other than that, that's it. This is very, very simple stuff compared to some of the other things that we've done. All right, so now let's put it in context and try to do some things. So an object starts from rest at the point 1, 2, 0 and moves with an acceleration of that. Find the location of the object at 2 seconds. So they give me acceleration, they want location, which is position. This is the second derivative. I need to take 2 antiderivatives to get back to the location that I need. So my acceleration vector, let's see, is jk, which means 0, 1, 2. So then my velocity vector is going to be c1, t plus c2, and 2t plus c3, because I had to take the antiderivative of 0, 1, 2. And then it says the object starts from rest. So v of 0 is supposed to equal 0. So if v of 0 has to equal 0, this has to be 0t, 2t. Hopefully that makes sense. And then my position, we'll call it r of t, is the antiderivative of that, which is going to be c1, and then 1/2 t squared plus c2, and then t squared plus c3 when I take the antiderivative. It says it starts from the position 1, 2, 0, so at t equals 0, I should be at 1, 2, 0, which makes this 1, 1/2 t squared plus 2, and then t squared for my final component. There's my position vector, and we wanted the position at 2. So I'm gonna, plug in 2. 1/2 of 4 is 2, plus 2 is 4, and 2 squared is 4. And yeah, I mean, that's it. So tell you what, on this last one, I'm going to be quiet and do the problem in a speedy fashion, and then you can look back and check your work against mine, and I'll do a quick recap. So what I did here is I took the antiderivative with my C1, C2, C3, and then since my initial velocity is 1, 0, 1, what that means is when I plug in 0 for t, I need to get 1, and the cosine of 0 is already 1. So that's why there was a plus c of 0 here and there, and then 2t plus 1 for the final. And then for r of t, I again took the antiderivative, c1, c2, c3, plug in 0, and I should get 8, 1, 4. So when I plug in 0, c1 has to be 8, c2 has to be 0, because the cosine of 0 is already 1, and then c3 has to be 4. Now, we are going to start talking about projectile motion here, and just to kind of give us a big heads up with it, there's a formula. If you want the position function for a projectile, something you launch, if you neglect air resistance, you have this formula right here, where r of t equals v sub 0 cos theta ti, and h plus v sub 0 sine theta t minus 1/2 gt squared j. Now, those of you who are physics aficionados will probably say, hey, I've done that in physics. Yep, you totally have. And this is where math and physics cross, and if you're lucky enough to be taking physics C, you've probably seen some of the connections between calculus and physics. But my question here is, why does that formula make sense? Well, if you think about it, x is my horizontal component, and that's v sub 0 cosine theta t, where my horizontal position depends on my velocity and the angle at which I throw something. Nothing else affects my horizontal position because gravity is just pulling me down. It's not pulling it left or right. Y is your vertical component. So h equals v sub 0 sine theta t minus 1/2 gt squared. And the reason that that guy makes sense is because I have a height that depends on my initial height, absolutely. I launch at an initial velocity with an angle, but gravity is pulling me down. Well, wait, how come we always take half of gravity? Why is that in the physics formula always 4.9 when gravity is 9.8 meters per second squared? Well, here's why. This is position. So velocity is the derivative of that. Again, I'm just doing the vertical component of velocity. That's the derivative. So my velocity is v sub 0 sine theta t, but take the derivative, the t goes away, and then the derivative here just becomes gt, and then my acceleration just becomes negative g. That's why all this makes sense, is if I have something, the only thing that's acting on me is gravity. When you take the antiderivative of that, your gravity grows a t, and it also grows a constant, which becomes your basically initial velocity, or your initial speed, really. And then when you go to find position, you take another antiderivative. Your g now has grown a t squared, but you need the 1/2 because of the add 1 to the power divide by the new power. So that's a quick intro to why you have 1/2 gt squared at the end and not just like g. All right, I am done yammering on. We did a Minecraft joke the other day, so we're going to do another Minecraft joke because, again, I have a 6.5-year-old who loves it. Why is the Enderdragon so bad at reading books? Because he always starts at the end. I know, it's terrible, but, you know, when a 6-year-old likes it, I figured I'd try it on you guys. All right.